Hi, welcome to this particular module. In the last module, if you remember what we have seen MEMS based technology, or you can say micro electromechanical systems, and in this module what I want to show it to you is the silicon, because silicon will be used as a substrate. If you remember, we are talking about 5 key concepts particularly in the MEMS domain, right, which were the microelectronics, microactuator, microstructures, microsensors, and now let us quickly understand what is silicon and how can we use silicon as a substrate. In particular, some of the parts you may see that we are repeating, but I want to quickly go through that particular section where you will be understanding how the silicon wafer looks like, and that is why I have brought silicon wafers with me. I will show it to you in few minutes. So, if you see the slide and if you remember, we were looking at the silicon bowls earlier, right, and then from silicon bowls the silicon wafers are fabricated, and as we know, this is a class 1000 or 100 clean room environment, right, and so to avoid any particles or any debris, right, onto the silicon wafer. Now, this is the process of fabricating or fabricating silicon from sand. So, we have also seen this particular technique where we were looking at the fabrication, where you start with a silicon which is polysilicon, right, and you introduce a seed crystal and slowly pull up the seed crystal. The rotation of the seed crystal will be in opposite direction to the rotation of the bowl or the holder or the crucible, and then when you have a ignite, right, you can go for trimming, and then you have a flat grinding. This is a primary flat. Now, what I mean by primary flat, I will show it to you in some time. Then you go for wafer slicing, edge rounding, lapping, etching, polishing, and finally wafer inspection. Alright. So, what is this particular flat? So, if you see in my hand, I am holding a silicon wafer. If you can see what I am holding, please. Can you show my hand, please? Yeah. So, can you see this flat here, right? This is a flat, correct. If the wafer is round, but there is a flat here, this is the primary flat, and all the wafers would have primary flat. So, this is one wafer, right. Let me use another wafer. Another wafer is right over here, right. Let me show it to you. Now, this is not a correct way for holding wafer, by the way. I am just showing to you because this is a demo, but otherwise you have to wear gloves, you have to wear tweezer, you have to hold tweezer to hold this wafer. You see this wafer again. What do you see? There is again a primary flat, right. So, all the wafers would have primary flat. Okay, this is what we were looking at the slide. So, if you see the slide again, you will see that the primary flat is there because of the flat grinding, and there is a reason of creating this primary flat. We will be discussing this in few slides. This already you know that we can use a diamond cutter to cut the wafers, and this is a lapping and polishing unit. This particular is a lapping machine. If you go to microchemicals.eu, you will understand the process of lapping. Now, let us quickly understand what are Miller indices. This is also your homework, that what exactly Miller indices are, but to put in a simple terms, Miller indices will help us to understand the crystal orientation. That means that whether this orientation is 0 0 0, 0 1 0, 1 1 1, 1 0 0, 1 1 0. So, what kind of orientation, crystal orientations are there within the silicon wafer? It is also called HKL plane or Miller indices, and if you see, then depending on the secondary flat with respect to primary flat or no flat with respect to primary flat. What I mean is, you see in this wafer, this schematic 1, 2, 3, 4, this all 4 are primary flats. All 4 are primary flats. Now, you will see a small secondary flat in some wafers. Is there a secondary flat in this wafer? Secondary flat, what is secondary? SECONDARY, secondary flat. Can you see in this wafer secondary flat? No. In this wafer, yes. Where is it? It is here. right. In this wafer, yes, where? Here. In this wafer, yes, where? Here, is not it. So, the first wafer is not having any secondary flat, while the second wafer, third wafer and fourth wafer, they have secondary flat. So, what is the use of having this secondary flat? Now, if there is no secondary flat, that means we can say that this is p type 111. So, you will understand that the wafer which will not have a secondary flat is having 111 orientation and it is p type silicon. If the secondary flat is at 90 degree with respect to primary flat, this is at 90 degree with respect to primary flat, then we say that this is a p type 100 wafer. If the secondary flat is at 45 degree with respect to primary flat, right, then we say that this is n type 111 wafer. If the secondary flat is at 180 compared to primary flat, we say that it is n type 100. So, what we learn from here? We learn that with respect to primary flat, wherever the secondary flat is there or if the secondary flat is absent, we can delineate or distinguish the p type from n type and 100 from 111 for all the silicon wafers. Alright, that is the advantage of looking at the Miller indices. Now, if you again see the wafer that I am holding, can you tell me what kind of wafer it is? You see, is there a flat anywhere else? This is a primary flat, right? And if you see little bit closely, then you will see that the secondary flat is here. Secondary flat is here. This is a flat. Okay. The if I cannot show it to you very closely, but if I hold it in this way, you will be able to understand. Yes, this you will be able to understand. There is a flat here and there is a bigger flat here. The big flat is a primary flat and the small flat is your secondary flat. So, if I have 180 degree, the secondary flat is at 180 with respect to primary flat, what kind of wafer it is? It is n type 100. Now, let me show you another wafer. You see this wafer. Here you have the secondary flat at 90 degree with respect to primary flat. If the secondary flat is at 90 degree with respect to primary flat, this is p type 100, right. Why? Because the secondary flat is at 90 degree with respect to the primary flat. You got it? This is how we can distinguish both the wafers, primary flat and secondary flat. If I hold the second wafer, then you will understand that this wafer is my n type 100, this wafer is my p type 100, because my primary flat is here and the secondary flat in this particular wafer is, this wafer is at 90 degree. In this wafer it is at 180 degree. So, 180 degree n type 100, 90 degree p type 100. Got it? This is how we can distinguish two different silicon wafers or a given silicon wafer. Alright. Now, another thing that you see, if I show you the back side of this wafer, it is grey, right, it is grey, right, and this is a polished side where you can see your you can of course not see your face, but you can see it is like a mirror. Is like a mirror, right. If I show you the ceiling, you can see the ceiling onto this particular wafer, isn't it? Look at the ceiling, right. That means this is polished side, this is polished side, but if I hold the wafer in this way, can you see the ceiling? No, you cannot. This is rough side. That means this wafer is single side polished silicon wafer, single side polished silicon wafer. This as well, but if you see the color of this one and color of this one, the color of this is different because there is a oxide. So, if I show you on the back side, you will see that this one, right, is having a different color compared to this one. This is like a gray color, this is not gray. That means this is without oxide, this is with oxide. Alright. When you grow oxide, the oxide is transparent, but because of the the light reflecting through that and absorbing through that, you can say that the color difference would be there. Alright. So, this is how you can also see whether there is a oxide or not. In any case, when you start with the silicon wafer, you have to dip this wafer in HF and then you have to go for a pre baking, so to you remove any humidity before you start any process. Alright, this is how it is. This is the cassette to hold the silicon wafer. So, you can use the silicon wafer. Again, let me reiterate that this is not a correct way of holding the wafer. For holding the wafer, you need to wear gloves, you need to hold tweezer, and with tweezer you have to show it. You have to wear a gown depending on what kind of laboratory you are working on, depending on what kind of experiments you are targeting at, but these are all very important factors. So, now if you come back to the screen, you will appreciate that why there is a secondary flat with respect to primary flat, or there is no secondary flat with respect to primary flat. So, let me play you this video and then we will continue.
You may not realize it, but we are surrounded by arguably the greatest, most revolutionary invention of the last 50 years. It's in TVs, stereos, watches, cars, phones, traffic lights, and pretty much every appliance in your kitchen. In fact, these days if a device uses electricity, it probably uses one. The tiny gizmo in question is, of course, the silicon chip. Making these extraordinary miniature electronic brains is one of the most complex manufacturing tasks ever attempted. So, how do they do it? Texas, USA. Home to big stuff. Big cows, big boots, big hats, big mustaches. But Texas is also the birthplace of a miniaturized miracle, the silicon chip. And here in Sherman, 20 miles north of Dallas, is the MEMC fabrication facility. In this strange, futuristic-looking plant, they produce silicon wafers, which are the basis for all modern microchips. Silicon has special properties because it's what's called a semiconductor. That means that depending on how it's treated, silicon can either conduct or block the flow of electricity. It's this property that makes it ideal for supporting the millions of tiny transistors necessary for a modern computer chip. But because these transistors are so incredibly small, the silicon base on which they rest needs to be absolutely flawless. It took decades to perfect the process of producing silicon with a perfect monocrystalline structure. They begin with raw polysilicon, or poly, and heated to over 2,500 degrees Fahrenheit inside a special sealed furnace, which has been purged with argon gas to eliminate any air. The resulting lake of molten silicon is then spun in a crucible, and a silicon seed crystal, roughly the size and shape of a pencil, is lowered into it while spinning in the opposite direction. As the molten polysilicon is allowed to cool, the seed crystal is slowly withdrawn at around 1.5 millimeters a minute. The result is a single silicon crystal weighing around 440 pounds and with a diameter of around 200 millimeters. The crystal is so strong its entire weight can be supported by a single thread just 3 millimeters across. But it is brittle, and it must now be cut down to size without shattering. After testing with chemicals and X-rays to check its purity and molecular orientation, it's fed to a silicon salami slicer. This 10-ton wire saw uses a fast-moving web of ultra-thin wire to produce wafers of silicon that are just 2/3 of a millimeter thick and 99.999% pure. Once cut, there are microscopic marks left on the wafer's surface, so it's time for a buffing using a process called lapping. After a twirl in this high-powered polisher, they are still not smooth enough. So they're given yet another buff using a chemical process. The result is wafers of silicon with a surface roughness of less than 1/1,000,000th of a millimeter. Buffed to a sheen, they're finally ready for etching with the circuit design. Coming up, how do they eliminate the biggest enemy of manufacturing in a microscopic environment, the common dust particle? Find out next on How Do They Do It? Packing millions of transistors onto these tiny silicon wafers is the job of chip manufacturers like Texas Instruments. Back in 1958, the inventor of the integrated circuit, Jack Kilby, managed to squeeze a single transistor onto his design. These days, the latest generation uses almost 1 billion, and according to Moore's law, that number doubles every 2 years. Of course, the more they try and pack into the design, the smaller each transistor needs to get.
There are over 250 million transistors in this design. Someone has to shrink them down to this.
Working at this microscopic scale exposes the chip makers to a major problem. When a transistor is only 1/10,000th of a millimeter across, the smallest particle of dust is enough to cause an electronic train wreck. So before staff members like Dane Bailey set to work in the fab, it's on with the bunny suit.
For our general product that we make here, a DSP, typically takes on the order of about 1,500 individual processing steps from start to finish.
With an area of just under 194,000 square feet, the fab is a Class 1 clean room. Thanks to 12,000 tons of air conditioning equipment, the air is 1,000 times cleaner than a hospital operating room.
There's actually less than 100 particles per cubic foot of air. As few as one particle landing on a critical area can kill a chip.
To give you an idea how clean this room is, walking alone produces 5 million particles every minute. So to avoid contamination from the inadvertently dusty staff, front opening unified pods, or FOUPs, transport packets of wafers through the intricate process of component construction. The key problem is miniaturizing the complex designs and imprinting them onto the wafers. It's done through a process known as photolithography. First, the wafer is coated with photosensitive chemicals which harden when exposed to UV light. In sealed dark rooms, light is shown through an image of the design, then through a miniaturizing lens and onto the coated wafer. When the chemical is washed off, the design remains, just like a developed photographic image. But in order to pack all the components onto the wafer, they are built up layer by layer, like floors in a miniature skyscraper. To complete the job, the FOUPs cycle the wafers up to 40 times, repeating the photo etching process for each new layer. Some layers are cooked, some blasted with ionized plasma, some bathed in metals. Each different type of treatment changes the properties for that layer and slowly forms part of the jigsaw making up the chip's design. The finished sheets of silicon wafer carry up to 1,000 individual microchips and billions of circuit elements. All that remains is to slice and dice, and the journey from sand to circuit board is complete. What was once a worthless pile of sand can now change hands for more than nearly $700 an ounce and calculate pi to 1,000 decimal places in the blink of an eye. Metaphysical poet William Blake reckoned he could see the world in a grain of sand. But if he were to look again today, he would surely be more amazed to discover a billion tiny transistors.
Alright, so in this video what we have seen? We have seen the how the silicon wafer or silicon substrate is used to form small chips. Now, same way we already have seen this slide where you can use the silicon dioxide as a field oxide, masking oxide, gate oxide, and it can also be used as a insulator between metal and semiconductor or as a masking oxides. Now, the HN for silicon dioxide is your hydrofluoric acid, or you can also say buffer hydrofluoric acid, BHF or HF. As we have seen, this can be used for common dopants, right. So, it can be acted as a diffusion mask, and depending on the type of the dopant and the temperature, the thickness of diffusion, the thickness of the silicon dioxide would vary, right. For example, if I am diffusing for 1 hour and if I am diffusing boron at 1200 degree centigrade, then I will require approximately 0.05 micrometer of silicon dioxide. This is what the chart shows. Dry oxidation, you know it, that dry oxidation is only with silicon and oxygen, while wet oxidation is the help of water vapor. When you have water vapor, there is a hydrogen gas which will also come as a byproduct. Wet oxidation is faster than dry oxidation, however dry oxidation is better. The quality of the insulator is excellent in case of dry oxidation, and in case of wet oxidation it is not, because the hydrogen gas that comes out of the film creates a path that electron can follow. This is the way that you calculate the growth of silicon dioxide on silicon, and how much silicon will be consumed, and this we have seen that there are several thermal oxidation methods, right, for growing the silicon dioxide. Now, if this is the let us quickly again recap. This is the thermal oxidation system, and here there is a horizontal tube furnace. That furnace are in the horizontal position. This is a vertical tube furnace. The furnace is on the vertical in the vertical manner, and the dry oxidation, this is a furnace, right, and this single lines that you see here like this, these are all wafers, is a silicon wafer. Okay. So, initially you do not want to grow any oxide when you are loading the silicon wafers. That is why what you do is you close this valve and open nitrogen. So, now your furnace will only have the nitrogen inside this particular horizontal tube furnace, and when you load the wafer, there will be no growth of silicon dioxide. Once you load the wafer and the temperature is achieved, what you do? You switch off the nitrogen and switch on the oxygen valve. So, then oxygen will react with silicon and form silicon dioxide. That is why it is called dry oxidation. In another case, you have the same furnace, but now in between there is a heater mantle which is also called a bubbler, and in which you have the water. So, you will heat the water and the water will boil and water vapor will be created. Initially, when you load the wafer, your nitrogen is on, this is off, this is off, this is on. That means the nitrogen will flow, and of course, oxygen is off. So, nitrogen will flow to the furnace. Alright. Now, next, when you load the wafer and temperature is achieved, what you will do? You will close the nitrogen, you will close this valve, you will open this valve, this, and oxygen. What will happen in this case? Oxygen will flow through the bubbler, carry the water vapor into the furnace. This will cause a reaction of silicon dioxide with H2O. If you balance the equation, it will be silicon dioxide plus 2H2O, which you have seen here, right, gives you silicon dioxide plus 2H2. So, this is the method. While there is one more technique which is called cryogenic oxidation, in which you have oxygen, you have nitrogen, you have hydrogen. Now, what you do is initially you close oxygen and hydrogen valve, only allow nitrogen to flow through the furnace, and then later on what you do is you close the nitrogen valve and open the oxygen valve and hydrogen valve. Oxygen will flow here, hydrogen will mix with oxygen, which is H2, and it causes the H2O2 vapor, which will cause the silicon dioxide to grow on silicon. Now, wet oxidation is using H2 and O2 like this particular fashion is more cleaner and popular than using the bubbler system. Okay. Now, here you can see that wafers are loaded onto the into the quartz tube inside the furnace, and the heating coils are there, right. Oxygen or water vapor flows through the reactors and pass the silicon wafers, and the typical velocity is about 1 centimeter per second. You can also look at it through the textbook from which is silicon village technology by Plummer, Deal and Griffin, and you can also look at the Waterloo University ec.waterloo.ca, where they have given the details about the thermal oxidation. Now, let us see this video where you will be actually looking at how the thermal oxidation system works. So, now you have seen the video, right. What you look at the video, you have seen how this oxidation system can be used for growing silicon dioxide using wet and dry oxidation. So, this is how the from silicon to silicon dioxide, that is what we have shown the wafer, how the wafer with silicon and how the wafer with silicon dioxide looks like. Alright. So, till this particular class you need to understand that how silicon and silicon is fabricated and how silicon dioxide is grown, and in the next class let us see some characterization tools to understand how you can measure the thickness of silicon dioxide. Till then, if you have any questions, feel free to ask me. I will see you in the next class. Bye.